Let's try this problem. You give it a try first, read through it, do analyze, plan, compute, evaluate, and see if you can come up with something. Stop the video and try and get the answer to this question. I'll come back in a minute and help you out. Okay, here's how we can solve this problem. Let's take a look at the basic facts here. Here's what we know. We know the pool ball has a mass of 260 grams. Most of the time in physics we want kilograms, so it might be more sensible to write this down as 0.260 kilograms. That would be the conversion. Apply dimensional analysis. If you don't know how to do that in your head, that's fine. But a lot of us can do those kinds of calculations in our head now. Okay, the guy applies constant force on the ball. So the whole time he's pushing this force never changes. And during that time, he's moving it this far, 30 centimeters. When the ball leaves his finger, it has a velocity of 1 meter per second. The question is, what was this force here that the guy was applying to the ball? Well, what do we have here? We've got mass, we've got a final velocity, you could call that VF. We have an initial velocity. It says it was initially at rest, so that means VI was 0. And we've got a distance. Well, with all those things, I think we can figure out acceleration. If we can find acceleration, we can get force because we know the mass. Force is mass times acceleration. Well, let's do the acceleration thing first. Again, I'm going to switch to a different medium to solve this because I think I need a little more space. Well, here's our situation recreated here on this notepad, and I've got 0.26 kilograms for a mass, recall. Force is what I'm trying to find here. That's my objective. It starts out with an initial velocity of 0. It ends up with a final velocity of 1 meter per second, and it does this change over 30 centimeters. Well, most of the time in physics, we're going to work with meters to make the units all come out, right? So I'm going to change my 30 centimeters to 0.30 in meters. What do I know here? This is a D, this is a VF, this is a VI. I know a mass, and if I can find acceleration from all the rest of this stuff, I'll be able to get force, because force is mass times acceleration. Well, I think I do know how to relate initial and final velocity and acceleration and distance through this equation that we've worked with before. VF is equal to the square root of VI squared plus 2 times A times D. Now in this situation, we know that our starting velocity is nothing, so we can just make that term go away, and this simplifies this equation a bit. We can write down VF is equal to the square root of 0 plus 2 times A times D. So that means, if we square both sides, that VF squared is equal to just 2 times A times D. So if I divide both sides by 2 times D, here's what I get. VF squared divided by 2D, well, that's equal to my acceleration. So let's plug some stuff in here. My final velocity is 1 meter per second, and I'll square that. That's divided by 2 times this distance, which we know is 0.30 meters. Here's why we had to convert it to meters, so that they cancel here. Let's take a look at those units. We're going to have meters squared per second squared on the top, and on the bottom we're going to have meters. So that'll end up being just meters per second squared, and that's a good unit of acceleration. Let's do the arithmetic here. 1 squared is just 1, and we're going to divide that by 2 times 0.3. And what we come up with is 1.7 approximately. So we're going to write down 1.7 meters per square second. Alright, so going back here, we can finally figure out what we really need in the end, and that is force. Force is equal to mass times acceleration, which is equal to, in this case, 0.26 kilograms, because that was the mass of the ball, times the acceleration of 1.7 meters per square second. One last calculation here. 0.26 times 1.7. There's our final answer. The force on this pool ball was 0.442 kilogram meters per second squared, which is 0.442 newtons. That's probably more digits than I really should have. That might be a little better.